Okay, good. Sounds good. So this is our third week of a semester. So out of 5 week of summer session, 40% of the semester is gone. So we're done with 40%. We just have 3 more weeks to go. And I don't. We have no exam this week, but we have an exam next Tuesday. So I want you to be paying attention to the topic, and you should be on top of everything. So I have finished all the grading of your exam, and for those of you who submitted online, I have uploaded the graded paper. So accidentally, I did upload the paper you submitted. So I did it again on my second time. So you may be able to see two different files in your. I think all you have to go is go to your grades, then check the comment section. I think that's how you should be going into. So you go to your grades, and under the exam one, you may be able to find a comment. And if you click on the comment, you will see the file that I have uploaded. There may be two of those, and one of them is the file that you submitted. So the other one, the second one that I uploaded, that's going to be the paper that I have graded. So then you can see what you missed and what you did it correctly. So of those questions, let me just say one of the questions on that exam, I had a typo so that the student online, your question is perfect fine. But the question number 7, but on paper, I was changing my question right before the exam. So I was correcting it and modifying it, and I just forgot to do some last modifying. So the question number 7 for for you on Zoom and the student in classroom, they're a little different. And because of that, I looked at the question on my paper and I might have given you the wrong hint at the time. So anyway, there was a lot of confusion there. So I did not grade. So this question number 7, whether you have done it correctly or you didn't, I just didn't grade. So this is a question that I skipped, so I didn't even look at it. So if you're doing online and if you have the correct question, then it's harder than the question on paper. So I think that's the one that's not fair to grade the question. And I might have given you the wrong hint. So this is supposed to be the union. And I think I have the paper intersection and I've given you the wrong hint at the time. So that's the question that I didn't grade. So your exam is 50 points total. So your points is how many points you earned out of 50 points. All right, so that was that. Just want to make sure that you know that. And the second exam is pretty soon, so I'm going to be seeing the topics. So under the exam number 2, which is on Tuesday, July the 22nd, I have the list of topics, so it might be a little easier for you to organize what you have to prepare for the exam. So these are the things that I made this afternoon. So I might add or modify, but I think this is a thing that we completed so far and we will do after this today's class. So I have big topics one by one, and I have little sections. 3.1 means under section 3.1, and 3.2, and 3.3, and 3.8. So these are the sections that the topic appears. So you might want to go check this out before you take the exam to see if I have any understanding of the question of this type. So your homework question is basically these questions. So can you get this PDF using, or can you get the CDF using PDF? Or can you get the PDF using it? So anyway, all these questions are right here. So this is things, so you might want to go check this topic for exam 2 as we move on. So right now we have finished 3.1, 3.2, and 3.3. So all these topics, the big topic number 1 and 2, you should know how to do them. So you do your homework assignment question, and you should be able to do all of those, except 3.8, which we have to do a little later. All right, so I think as we move on, we are doing 3 point. I think we did a little bit of 3.4. So you can go list of things, and you ask yourself, do I know how to do this? Do I know how to find a constant of a joint PMF and joint PDF? Do I know how to get the CDF out of the joint PDF? So these are all the questions you have to ask yourself. And on the exam, there are lots of integration you have to do. I want complete answer on the exam. You cannot skip it. You cannot use your calculator. That's not impossible. You have to show me every single detail on the exam, so you be prepared. So on your homework assignment, you may have to do everything before you do it, so that you know exactly what to do when it comes to the exam. Any other particular question before I go and continue? I have to go 3.4. All right, so let's then move on. So I think okay, let's see where we are. So I think 3.4. Okay, got this. So let me go back to the beginning of 3.4. So 3.4, section 3.4 is all about joint distribution. So we are looking at two variables together at the same time. So x can be a variable, random variable, can be discrete or can be continuous. And there's another variable, y variable, can be discrete or can be continuous. So we only do either both discrete or both continuous.
Check.
So we are talking about the joint distribution. So if they're both discrete, we call them joint PMF, probability mass function. So that's my f of xy. So this is nothing more than the probability. So joint PMF, or anytime you have the PMF, this is the probability itself. So it gives you, when your x variable, the x takes the number small x, the y takes the value of small y, then fxy gets me the probability of that happening. So this is a joint PMF. This is for discrete case. And because it's joint PMF, typically we show you the PMF as a table like this, very common. So we have talked about PMF, and the PMF means the probability of all these possible xy pairs. The sum of all these must be 1. So that's what this is about. If I add all the probabilities for all the xy pairs, must be 1. And if I want any probability that your x and y is an element of a set C, any ordered pair C that you're interested in, then you just have to go get all these xy pair that satisfy the condition and add them up. So we did probability of this. So x is 2 or higher, and y is 1 or less. So x can be 2 or 3 in this case. Y must be 1 or smaller, which is this. So any xy pair, so these are the two xy pairs. So x2, y1, x3, y3, you add them up to get the probabilities. So that's how we do the probabilities using the joint PMF. We got them. And finding constancy, it's then the very typical question you have to know. And we did a continuous case. So when x and y are both continuous, we have fxy, which is the joint PDF. This is not the probability, this is actual function. So when you integrate this function over some region, dx dy, that will get you the probability. So you do integrate to get your probability. That's a joint PDF. So I talked about the joint PDF. So that should be some function of joint PDF. This is my f of xy, something like this. And over a particular region of x and y, we can imagine the volume under that joint PDF function. The volume equals the probability. So you have to get your integration, double integration, to get your actual probability. So that's how we did it. It's the same thing. So joint PDF is a non-negative function, and your entire volume under that function over that support, that should be 1. So that's what we talked about, finding a constant. There must be a particular number C Otherwise, it cannot be a PDF. So we have talked about finding the CD so that this whole function becomes a joint PDF. So we did all these calculations last time. And then where we were, and then we finding the probability. So finding the probability must be finding the volume over that XY region. So we did that, got this, and and then we did the CDF, the cumulative distribution function. So by definition, it's the extension of this CDF of a single random variable. It's exactly the same. So I'm looking at the jointly x and y, so big F, x and y, that must be the probability that your x is less than or equal to small x, your y must be less than or equal to small y. So we have to get this entire probabilities up to x and y, smaller than or equals to x and y. That should be your CDF. So I have shown you the CDF for the discrete case, which I can only do a few cases. So x is up to 0, y up to 0. You can add all the probabilities up to that point. That should be your f of 0, 0. But it's not easy to have entire CDF for the discrete case. So we may not want to do that. This idea is there. For continuous random variable case, it's not adding the probabilities. You're integrating your function up to this x value for x and for y value, and you have to do the double integration to get your CDF. And you go backward, you take the derivative of your CDF to get your PDF. So I have to go the partial derivative of your CDF. So 1 for x and with respect to x and with respect to y to get your actual joint PDF. So I think that's what I stopped last time. Okay, so why don't I, let's see where I should be going. So why don't I go into, let's do this example first and I'll go from there. So let's do this example. Let's get this PDF using PDF. Let's get it. So I have one example. So I'm going to be giving you an example. So this joint PDF. Of x and y is given below. So fxy is equal to 2 times e to the power of negative x and times e to the power of negative 2y. And the support of this distribution is for both x greater than 0 and y greater than 0. Otherwise, this density function equals 0. So that's where your x and y both must be positive. So that's when your density function is non-zero. Otherwise, all 0. So that's when I see my density function. So I want to find the joint CDF. All right, so you have to imagine your support of this function of the distribution is this. So x positive, y positive, and you have this joint PDF. So I have to imagine the support. So here's my x's and y axis. So my support must be all these. So something over here. So it's both going to infinity. So we have all this region, and I have my density over that region. So let's find the CDF. So let's get the joint CDF. So I'm thinking of having the CDF, which is, again, let's get the x and y for both greater than 0. And below 0, there's no probability anyway. So that's 0, 0. For x positive or for y positive, the CDF, by definition, it's the probability that your random variable x is less than or equals to some number x, And also your y, the random variable y is less than or equals to the number y. So we have this probability under this density, x is less than or equals to some small x, and y being less than or equals to small y. So what I can imagine is doing this integration. So your x and y, so let's go, your y value is going all the way up to y from negative infinity to y value, and your x is from negative infinity up to this x value of your joint f of u, v, du, dv. So this is more of a definition. I'm just writing a definition. So this is a joint PDF. All right, so the rest is calculus. So I'm going to be going to the double integration from negative infinity to some number y, and negative infinity to some number x. But I don't have to go from negative infinity anymore because this entire joint PDF has no probability below zero. So now I can go change my lower bound from zero to some number y. And same goes from zero to some number x. And the joint PDF is 2 times e to the power of negative u and the power of negative 2v du and dv. So that when you do this, you will get, so they're so totally separated, so you can actually do this. I'll just do the step and you do the rest of it. So it will be, anyway, at the end of it, from 0 to x, you will get e to the power of negative u du, and you get from 0 to y, and 2 times uv dv. So you'll get something like this. And you will have a function which is 1 minus e to the power of negative x, and times 1 minus e to the power of negative 2y. So you do the rest of it. So this is my CDF. So to be more clear, so you get the f of xy has this function, 1 minus e to the power of x, 1 minus e to the power of negative 2y, for both x and y, 0. Greater than 0, otherwise it's 0. So this is a proper CDF. So again, you have to imagine the CDF is nothing more than doing, well, here's my x and y, the values of x and y, and your probability that, let's just do it this way. So this is a random variable x, to be more exact. So that has number x somewhere, and y somewhere. So that's my x and y. And we are trying to figure out the probability of x is less than or equals to this number, and y is less than or equals to that number. So we are actually trying to get the volume of this joint PDF over that region. So that's what I can see the joint PDF to joint CDF. Are we good so far? So let me show you, I think I pictured for you just in case. So this is what I have it. Let's get it done. So this is the example that we just did it. Let me do the rotating. So this is my x, and here's my y. So this is my joint PDF. It looks like this. So this is my joint PDF. And what we are trying to do is we are trying to figure out the volume. So remember, the entire volume under that joint PDF, it has to be 1 no matter what. Are we good? So that was that. What we are trying to do is we are trying to get the volume. So this is nothing more than volume. Your joint CDF is nothing more than, let's pick x. X can be any number. And let's pick a particular y value. Can be any number. So in my Desmos picture right there, what I have is I have a value, which is, let's get this. And I have my b value. So a is my x values. X's are changing, and your y's are changing also. There you go. So here's my x values. So we are trying to get the volume, but x is smaller than equals to this a number, and y is smaller than equals to this b number. So right now, my a is, let's say, 0.4. B is 0.2. So we are trying to get all these probability where x is lower than 0.4 and y is lower than 0.2. So I'm trying to get the volume under that density function. So that value is f of big F of uh, 0.4 and 0.2. So if I get my x values are changing over here, so a being this x value being 0.5, so I'm trying to get the whole volume under the density function, and that's really your big F, the CDF function value, and same goes with my y values. As I might change my y value, it gives me the volume. So that function value of the CDF is the volume of this, depending on your A and B. Matthew, do you have any questions?
Uh, yeah, it's just in terms of the integral. I saw that you split up the 0 to y and 0 to x.
Mm-hmm.
How do you know like where to put the one with the u and the part with the v?
Oh, which
Yeah,
one
I'm
is
just
you?
confused how you
So
split it up.
this is my x. So that's my x. This is my y. So this is my y.
Okay.
Mm-hmm.
Okay, so you just associate them with x and y,
Mm-hmm.
basically.
Correct. But the way I did it, I used my x and y. So that's my
Oh,
u and v. Mm-hmm.
okay, I see what you did now. Okay,
Mhm.
thank you.
So anyway, that's my CDF. So that gives you the volume of the function is giving you the entire the volume under the joint PDF and up to this x and y. So that's the whole CDF thing. So that's something that I did it. So now I did it. Let's moving on. So
I have a quick question too.
yes, yes.
Sorry, it's been a long time since I did like integration stuff, but
Mm-hmm.
is it just a rule like when two like functions are multiplied, you could just split it up and
Oh,
that's
I just did it because, well, I just have to do this. If I do my integration over here with the du, so the v itself is like a constant. So I don't have to worry about this or that number, and that's a constant, which I can take that out. So I can have to do only the variable with the u only. So after the integration, this is going to be basically inside your integration. So this whole thing is after I get my 2 times the constant times e to the power of negative 2v, it's out of the inner integration. So that's what it's right there, du.
Okay, thank you. That makes sense.
Mm-hmm. All right, so now let's get one of the theorem, which is 3, 4, 5. So this is saying, so with x and y, have a joint CDF, which is big F of x and y. It gives you big F with subscript x of x, which is the CDF of x. And it is the limit as your y value is approaching infinity, your joint CDF. So your y is approaching infinity, so I don't have to worry about y value, except with x alone. And you get the same thing for f of y, which is the CDF of y. And it's the same thing with the limit as x is approaching infinity, your joint CDF. So that is f of x and f of y. So we are going to be calling this, and you will see in the next section, we call this the marginal CDF. of x. So x alone. Same goes with this. We call this the marginal CDF of y. So y alone. So that's the marginal. So we have this. So in my example, instead of doing it limit of this function, the CDF, so we will see a notation as, so instead of doing this, make it simple as the joint, your y is approaching infinity, so we'll do it as f of x and infinity. So y value is approaching infinity in that way. So same thing with the marginal CDF of y. So we'll write it as your x is approaching infinity, so infinity, comma, y. So that's how it's going to be written. All right, so let's get the marginal. So let's get the example in the book. 3.4.14. So many of these examples are going one way or the other. So from this, get the other. From this, get the other. It's going back and forth. So this question is again, we said we have x and y continuous random variables. With x from 0 to 2 and your y being from 0 to 2. Let me do it over here. Let's do it then. So both x and y's are 0 to 2. So now this time I'm giving you a joint CDF. So the joint CDF of x and y together is given below. So your big fxy equals 1 over 16 x times y, and in parentheses times x plus y for x values and y values from both 0 to 2. So remember, this value function value will give me the volume under the joint PDF up to x and y. So anyway, let's get a, find the marginal. So find f of x, marginal CDF of x. All right, so for only, let's get this, x values from 0 to 2, that's what I'm interested in. Below 0, there's no probability. Anyway, from 0 to 2, your f of x, by definition, it's the probability that your x variable, random variable, is less than or equal to some number x. So this is nothing more than y value is anything. So we're interested in your y value, which is basically anything. So if you think of it as the probability that your x is less than or equals to the number x, but your y can be anything. So y can be anything. So think of it y being less than infinity. So any y value satisfies this. So because of this, we can think of it as this is a CDF, a joint CDF, x up to some number x, and y value all the way to infinity, like this. That's how I did it. The limit of that joint CDF. Now this, it's not difficult. Well, if you look at this CDF, I want to go back to the previous example. I think we did, where did I do? The CDF. When I did the CDF, right here, over here, for example, I have my joint, that is a regular PDF, which is 1/2 from 0 to 2 and 0 otherwise. So I get my CDF here. So I'm adding all the probabilities up to a particular point. So this entire area is the value of the function over here. so that once you get hit all the way up to 2, I have all the probabilities, so that must be just 1. And after this, there's no probability to adding, no cumulative probability, so it stays 1 forever that way. So therefore, if you think about the limit as x approaches infinity, the limit according to this is that number 2 anyway. So at 2, you get number 1, and that's your limit anyway. So therefore, what happened is over here, whoops, I think I have a join, not this. So this is exactly the same as, well, after 2, there is no probability to add. So now I say this, so that's y value is less than infinity, it's approaching infinity, but there's no probability after a y value of 2 or greater. So there's no adding probability after 2. So approaching infinity doesn't really matter. You end up with f of x, and y value of 2 will be 2 or 3, or doesn't matter, it will be exactly the same as, oops, my mistake, not y, it has to be 2. So f of x comma 2 is exactly the same as the y value of 3 or 4 or 5 or of course infinity, exactly the same. So never ever adding any probability after this point. So this is my CDF. So now I'm getting it. So here goes my CDF, the function, and y has to be 2, so that should be 2, and that should be 2 to get the actual marginal CDF here. So that should be 1 over 16 x times y being 2 and x plus y, x plus 2. So this is it. So I can do some simplifying. So therefore, your CDF, let's get the proper CDF. So that function, it is x over 8. Let's just do 1 over 8. X times x plus 2. So that is my CDF for x value from 0 to 2. For any other values, for example, x below 0, and this is for 0 to 2, and for the values greater than 2, so we have 0, anything x below 0. From 0 to 2, I know this function, this is 1 over 8, x times x plus 2. Then once you hit 2, we're done. So no more probability. So everything else becomes 1. So after 2, it's going to be 1 and 1 forever. So that's your marginal CDF. So your CDF, according to this, the graph looks like this. So you get 0 below this, below 0, and then you get a curved function like this, and then you get 1 after this, so this must be 2, and that should be 0. So that is your CDF. That should be 1. So the same way you can figure out your CDF of y, so you can do it on your own. So check yourself. Your CDF of y will be exactly the same. So you get 0 for y value less than 0, and the same exact function y times y plus 2 for y value from 0 to 2, and 1 for all the value greater than 2. So that should be it. So check this out. So that's my CDF. I know my CDF. So now let's moving on to B. Find the probabilities. It's a question always. Give me the probability. So let me find the probability that x is less than or equals to 1 and y is less than or equals to 2. What I have is a CDF. Well, isn't it easy? So I have this. Well, this probability is exactly the same as f of 1, and 2. So all the probabilities up to 1 for x and up to 2 for y. So this is my f of 1 and 2. So that's how it's defined. So therefore, all I have to do is using my joint CDF, which is 1 over 16 right here, x times y times x plus y. So x times y, so 1 times 2 and 1 plus 2. So that should be done 3 over 8. So this is your probability. All right, so let's get just one more. Then I'll be moving to the next section. Let's get C. Oops. So I want to find the probability that x is greater than 1 and less than or equals to 2. It has to be in that particular x value, and your y value is the same, greater than or equals to 1, the 1, but less than or equals to 2. So I want that probability. All right, so if I remember how to get the CDF, so whatever the CDF, remember when you get my CDF, what we're trying to do is I'm trying to figure out in my support is from 0 to 2 anyway, and we have some 2 and 2, this is my x and this is my y, so we have a joint CDF above this, and the CDF is trying to get you, for this particular case, we are trying to get this volume of that joint PDF. I don't have the joint PDF, but it's about the x value up to 1, y value up to 2. So nothing more than finding the probability over that xy region. So that happens to be 3 over 8. So in the same way, what this question is saying, I want the probability of your xy values. So again, my support is 1 to 2, 1 to 2, so 1 to 2, 0 to 2 for both x and y. And this is saying I want my probability that your x is greater than 1, but less than or equals to 2, and y is right there, right there. So I want the probability over that region. So that's what it said. All right, so I can do this. However, the CDF doesn't do this. CDF is giving you up to this 1 or up to 2. It only give you x or smaller. So we can make use of the CDF. So this is how I could do. So let me do some thinking. So here goes. In order to find the probability from 1 to 2, y being 1 to 2, I can do f of 2, 2. So what I'm trying to do is on my xy support, I want all the probabilities over this region, which is just 1 anyway, but I want that. And from this, I'll be subtracting f of 1 and 2. So what I'm trying to do is this is the volume over this region, and I'm subtracting because I only want that particular area, that little piece of this rectangle there, on the volume over that region. So I'm going to be subtracting 1 and 2 means your x value is 1 and y value of 2. So that should be the area over here. This is 1 and 2. So from this volume over this first big region, 2 by 2 region, and I'll be subtracting the volume over this region. This is 1, and that's 2, and that's 2. Then I'll be taking out that volume from the bigger part of it, and I'll be subtracting also f of 2, 1. Which is, again, I'm subtracting This is my 2 by 2, but this time I want my x is 2 or smaller and y being 1 or smaller. So it should be the volume of this region right here. And if I do this, I'm subtracting the volume over half of this part is gone, subtracted already by doing this. And I'm subtracting half of this part, the volume, subtracted it. When I do it, I'm subtracting this little piece twice. So I'm going to be adding that little piece, which is f of 1 and 1. So that means, so this subtracting and subtracting, then I'm going to be adding the volume from 1 to 1, 1 by 1 over here to there. And that gets me that little volume over that region. So that's what I want to do. So therefore, the rest is plugging in the value. F of 2, 2. So it's 1 over 16. X times y. So I think we got this x2, y2, and x plus y. That's 4. And then you do the same thing. So 1 over 16, x, y, and x plus y. That's going to be 3. And subtracting 2 times 1 times x plus y and adding 1 and 1. So 1 times 1 times 1 plus 1, that's 2. So that will get me the entire probability, which I think this is 1 minus 3 over 8 and subtracting 3 over 8 and adding 1 over 8. Which is 6, 5, 8, 3 over 8. Are we good so far? So that's how we do the probability with the CDF. So now that I've gone through this, the final question, this is my A, B, C, this is C. So let's get my D, the last question. So now I want to get my joint PDF. So I have my joint CDF. So how do I get my joint PDF? So f of x and y, the PDF is a partial derivative. So you go, you do the derivative, the joint CDF, one with respect to y and with respect to x, for those x value from 0 to 2. So that gets me, the function is 1 over 16 x times y. So I'll be expanding it. So this is my CDF. So x squared times y plus xy squared. So you do the partial derivative, which I'll let you do it. So you will get, at the end, 1 over 8 x plus y. For x values, both 0 to 2. So I think this is getting your joint PDF from the cumulative distribution sheet. Any questions? So you do need lots of practices to get the solid understanding of going from where to where. Otherwise, you get so confused while they're taking these. So that's 3.4. So why don't I go a couple more concepts of 3.5 because I don't want to fall behind.
Can I finish writing? Okay.
Sure. It was the bivariate right here. Again, I have skipped a step. You can get this to this, so you'll have to check yourself how to get it, or can you get it yourself?
Okay, I'm done.
Mm-hmm. All right, let's go into 3.5, the marginal distribution. So I have introduced the marginal CDF already. So let's get the concept of marginal. So here goes the first subsection 351. So it's about the deriving a marginal PMF, probability mass function, or a marginal PDF, probability density function. All right, let's start from the marginal. So it's coming from the joints. Let's get the definition. 351. It's a marginal distribution. So it starts from the joint. You have a joint distribution. So you have x and y.
Check.
They have a joint distribution. So joint distribution means it can be joined PMF if x and y are both discrete, or it can be joined PDF when they're continuous. The marginal is, look at it alone. So I have this CDF already. So the CDF, the cumulative distribution function of one of the variable alone, x alone, that's called a marginal CDF. So I can go marginal CDF of x, and I can go marginal CDF of y, which I briefly did. In the same way, I can have the PMF, the probability mass function of one of them alone. That's called the marginal PMF of x. So the notation that you will see is that I didn't know which one is x and which one is y, so you have to be a little clear. So when I do my marginal case, you would want to have f of x as a subscript to know that this is x variable alone. Then this is my f small PMF, and you write x, so that it is about the x variable alone. And I can go the PDF of x alone, that's called the marginal PDF of x. So again, this is the same as f with subscript x, so that this is about the x alone. So that's the definition. So what you have to know is, how do I get it? So I have to know how to get this from the joint. So the theorem 351 is telling you how to get it. So this is about, again, x and y. They have a discrete case, x and y have a joint PMF. So the fxy. And it says, how do I get the marginal? So it says the marginal PMF of x, this is how we do it. So f of x alone, you're adding all these joint probabilities for all the y value, that's marginal. Then I can do the same for the marginal PMF of y value. The y variable is f of y. You add all these probability for the x values. So that's the marginal. Again, this question, the theorem is simply saying from the joint PMF, and it brings out to the marginal PMF. How do I get it? The joint, the marginal. So that's how I do it. So I'll give an example. Examples are way simpler than what it looks like. But I just want to make sure that your textbook is using a little different notation. So if you look at the book is using, I'm using f of x, which is pretty common, but the textbook is using f of 1 for x. And again, the book is using f of 2 for y. So the book is using 1 for x, 2 for y. I prefer x and y to be more clear. So that's a lot more common. So anyway, what it is as simple as, what time is it? 23. So let me get you one example, the introduction, and I'll stop there and give you a little break. So the marginal idea is as simple as this. The marginal probabilities, for example, when I say f of x is for x variable of 2, by definition, this is about the probability that x equals to 2. So 2 is 2, that's fixed. Y value, any y value, doesn't matter. So that means y can be anything. So it means that I want to add all these probabilities when x has to be 2, but your y value, any y value, so I'm going to be adding all these y values for any pair 2 and whatever the y value, and all the probabilities. So that becomes this f of 2 comma y for all the y value. That's nothing more than it's pretty intuitive. So x is fixed, that's 2. Your y value, you get all the different y values, you get all the probability added up together. So this is fixed in that sense. The y value, you have to add all the other y values. So in the same way, if I get my f of y of 1, for example, it's a marginal. So I want my y value equals to 1, x value, whatever that's available. So that means I have to go get all the probabilities. X can be whatever that's available, but y has to be fixed at 1. So I'm going to be adding all these probabilities for any pair x and y has to be 1. So that's what the theorem is basically saying. You get all these probabilities. X can be any x, but y has to be fixed at 1. So for all the x's. So the y value, that's fixed. And I want to have all the other x values, you add them up all together. So that's fixed in that sense. So that's what it is, it's marginal. So keep that in your mind. So let me have a little bit of break. And I'll start from there. So 6:25. If you have any questions, let me know. Otherwise, let's have about 5 minutes of break and we'll continue at 6:30. So for students who took the exam in person, I have your paper. If you're coming back to classroom, either tomorrow or sometime this week, I'll give it back to you. If you have no other plan coming to the classroom, then let me know. Then I'll scan this exam paper that I've graded. I'll upload it so that you can take a look at the paper that you have to finish your exam. All right. It's about 6:30, so I'd like to continue. So hopefully you are back to your desk, and so we can do a little more about the marginal probabilities. All right, so let's get you an example of this marginal. So let's get the PMF. So here's my, I'm going to be using a new page. Here we go. So let's get the marginals. Let's get the joint PMF of x and y looks like this. So f of xy equals x times y over 27 for x values 1 and 2, and y values 1, 3, and 5, and 0 otherwise. So that's my joint PMF, and I want my marginal PMF. So let's find the marginal PMF of x variable. All right, so for this joint PMF case, it's a lot easier to look at the entire table of probabilities. So why don't I re-express it as a table? So in general, you will see the joint PMF as this table of values. Let's get this. So I have some x values and some y values. So I'll get 1 and 2 for, this is my x values. And I want to write my y values in the first row, so 1 through 5. So your values inside it should be your probability. So probability is x times y over 27. So x1, y1 is 1 over 27. x1, y3 is 1 times 3, so 3 over 27, and 5 over 27. Then I go x of 2, so y value of 1, so that should be 2 over 27, and 6, and then 10 over 27. So these are my marginal, the joint PMF. So when I add all of these numbers, it has to be 1. Anyway, let's get the marginal PMF. So what's the marginal? So let's think about the marginal. So I have my x values. X values are either 1 or 2. So I have to get the probability of x value of 1 and x value of 2. So what I have is my x values are either 1 or 2. So by the definition, your f of variable x, so take a value 1, equals 2. Your x is fixed at 1, but your y value can be 1 or 3 or 5. So there's a probability that your x has to be 1, but y can be any y value. Let's leave it as this. So which means x is 1, but your y value can be 1 or 3 or 5. So you have all these probabilities for all these. So I want to get all these probability of f of x is 1 that's fixed, but your y value can be 1 or 3 or 5. So let's get all the y values. So in this case, I'm getting f of 1, 1, f of 1, 3, and plus f of 1, 5. So y's are adding up. So I have my y values are this or this or this. X is fixed. So in that table, when x is fixed at 1, I'm actually getting all the probabilities of, let's get this out. X is fixed at 1, here's my 1, and I'm trying to figure out f of 1, 1, which is this, and 1, 3, which is this, and 1, 5, which is this. So I'm simply adding all these probabilities. So that's the probabilities. So add them up. So that gets me 1, 3, 5. That's 9 over 27. So this is 9 over 27. So this is the marginal probability for x equals to 1. So that sum, let me do the table over here. So you can add all these numbers, and you will get 9 over 27. And that number is called f of the marginal probability of x equals to 1. Nothing more than that. So in that sense, I can do the same thinking, f of 2, x value of 2. So x has to be fixed at 2, but your y value can be 1 or 3 or 5. So adding all these probabilities, x has to be 2, but I'm having all these other y values, add them up all together, so that in this case must be nothing more than x is 2 fixed, so I'm getting 2, 1, 2, 3, and 2, 5. So adding these, that will become your marginal probability of x equals 2. So this is it. So f of 2, 1, 2, 3, and 2, 5, which is 6, 2, 8, 18, so 18 over 27. So that's 18 over 27. So this is called f of x, which is value of 2. So that entire set of values in the side right over here, so we call this marginal probability mass function for x. Nothing more than this. So this is it. So I have this whole thing. So this is your f of x. So that's what it is. So we typically write them as, well, here's my f of x. When x equals to 1, it's 9 over 27. I can simplify, which is 1/3. And when x equals to 2, it's 2/3. And 0 otherwise. So this is called marginal PMF of x. So when I add these two numbers, it must be 1 also. So simple as this is a marginal. Are we okay so far? So in that sense, I can do the same thing for the marginal PMF of y. I don't want to do it separately, but let's just do it over here. So if I go think about the PMF of y, let's do it over here. So if I do f of y, y can be 1, y can be 3, or y can be 5. So I'm getting this time when y value equals to 1. So that's 1, that's my y value of 1. So I'm going to be adding these two to get a value of the probability. So 1 plus the 3 over 27. So that's 3 over 27. That's your f of y value of 1. So we have entire probability in that way. So 3 and that's 9 over 27. Then we have 15 over 27. So this is f y value of 3 and y value of 5. So that entire set of three numbers, that's your marginal PMF of y. So that's it. So that's when we get the marginal. So it happens to be in the margin of the table. Now let's get this for this particular example. I could do a little differently because according to this, my marginal is adding the joint for all these y values, and I happen to know the marginal PMF, which is given as this. So for this question, I could actually use that. So here goes my join PDF, which is x times y over 27 And I want all these y values for any given x, and y value is either 1 or 3 or 5. So I'm going to be adding, in this case, so x over 27, your y value can be 1, so that should be x and 1, and then x and 3, and then x and 5. So I'm getting the 3 xy pair in that way. So I'm getting 9x over 27, which is x over 3. So instead of having this separately in this case, I could have done this as a mathematical formula. It looks like we have x over 3 for x value either 1 or 2, and 0 otherwise. It will be the same. But it's not typical. This is kind of general example. It doesn't happen in many other cases. It's particular, a very special case that I could do this. But anyway, when you have time, check yourself. When you get the marginal PDF of y, then you will get y over 9 for y values 1, 3, and 5. So do yourself so you can get them, which is not very difficult. So this is the discrete example. So I know how to get the discrete case. So let's moving on to the continuous. So that's your theorem 352. So now this time your x and y are both continuous. So x and y, they have a joint PDF. And it shows you, how do I get the marginal? Let's get the marginal PDF of x alone. So we write them down as f of x with subscript x. So instead of adding over all the different y values, we integrate your joint PDF with respect to y. So it's like adding over all the different y values for all these x, depending on support, but that's what it is. And the same way, the marginal PDF of y is about the same. Y is f of y. So you do add all these different x values, so you get the joint. So now you're integrating with respect to x. So that should be your marginal PDF. So a lot of integration you should be doing. All right, let's get this. So now I have this. So this question is again telling you, how do I get from the joint PDF and the marginal PDF? It tells you how to do it. All right, let's see how to do it. Let's get an example. So here's my joint PDF. It is given by the following. So f of xy, it equals to 2 over 3 times x plus 2y. For your support, your x values from 0 to 1, and the same y values from 0 to 1, and 0 everywhere else. So this is my joint. So I want my marginal. Let's get the marginal. The marginal PDF of x. So let's get the definition. The definition says the marginal f of x equals, you integrate your joint with respect to y. So here we go. Definition of it. However, you have a support. You always have to pay attention to your support. So where your density function is not zero, otherwise it's all zero. So I'm looking at my support in this case. So we have this xy value is 1 by 1. This is my x and that's my y. So support is this. So I have to integrate this joint PDF. So let's go through this. But I don't have to go through negative to positive infinity. I have to go your dy. It's only from 0 to 1. Your joint, which is 2/3 x plus 2y and dy. So I'm getting this, so now I'm ready to do my integration. So I'm getting my dy, so I'm getting 2/3 xy plus y squared. Your y value is going from 0 to 1. All right, so plugging in the value, and I'm getting 2/3 x plus 1. So properly, my marginal PDF of x equals 2/3 times x plus 1 for x value only from 0 to 1. Otherwise, 0. So look at the graph of the PDF of x. So it's only from 0 to 1. And here we go, 0 everywhere else. And it should be like this. And 0 everywhere else. So that's my marginal PDF. Are we okay so far? So it's any other questions?
I don't have any questions.
All right. So again, if you think about this entire volume and all these joint PDF things, I think I might have the picture. Let me just show you what we're trying to do. I think I have a marginal. The marginal right there. So this is the one. So we have this function. This is my joint PDF. Here goes. It looks like this. So over xy, both 0 to 1 right there. Otherwise, it's all 0. So we only have something over that region right here, on that region over here. And again, the entire volume under that PDF, the joint PDF is always 1. You know that. So what we're trying to do is, we are trying to figure out for a particular x value. For example, I'm going to fix my x value of something. So that's my a is my x value pretty much. So what we are trying to do is for a given x value, we can imagine getting this area under that function right there. So depending on your x value, you get your area under that function or that little thing, the green shaded area. So that's going to be the value of this, the marginal PDF, pretty much. Are we getting it right there? So that's what we're getting. You're integrating your join PDF over the dy, over the y values at particular x value. So whatever x is, that's what it is. And I'm going to be doing the same thing for the marginal PDF of y. So I'm going to fix any y value somewhere. The fix any y value right here under that PDF. And I'm trying to get to my y values are changing. As it changes, I'm trying to see the area. So that should be the value of your marginal PDF, pretty much, of the y. But that's exactly what we're doing anyway. So I did my marginal PDF. That's my marginal PDF of y. As a practice, check yourself. If I do the marginal PDF of y, this is an easy one because it's a rectangular area. So let's get the marginal PDF. of y. So again, by definition, f of y is you're integrating your joint. So I want my all these other x values or dx with respect to x from negative to positive infinity. But your x takes all the values of 0 to 1 in this case. So I only need to do from 0 to 1 of your joint 3 over 2, no, 2 third and 2 third. X plus 2y dy. Oh, sorry about the dx. Got it. So now I did one of it, so you can do the other one. So once you get this, you'll be able to get a function 1 over 3, 1 plus 4y. So your joint, the marginal PDF is 1/3, 1 plus 4y for y values from 0 to 1 and 0 otherwise. So that's the marginal one. So this is the one that's simpler version because your support is a rectangular region. So I just have to go your integral from 0 to 1 and 0 to 1 either way. That was easy one. So let me get you one, then I'll move on to the other topics. Let's get you the example in the book. It is 351. The example 353. 353 in the book. So it's a joint PDF is given. And the function looks like this, fxy. It is 21 over 4 x squared times y. For your xi's are, for x squared is less than or equals to y, and y is less than or equals to 1, and 0 otherwise. So your support is not just a rectangular region, it's a little different. So this is where your density is defined over that region. So I have to think about the support of the density, the distribution. So let's imagine, again, this is my x and y. Your y's are from x squared to 1. So looking at this, one side, so x squared is less than or equals to y. It's a parabola. So I'm trying to get a graph. Y is greater than or equals to that. So I have the function graph of it. It's going to be the parabola like this. So this is my x, and this is my y. So y is greater than or equals to this x squared, but y is less than 1, so 1 is over here. So my support, where the density is defined, must be somewhere over here. It's not a rectangular area. So that's my support. So I have to imagine this joint PDF above this region. So now I'm getting my marginal PDF of x. And let's get the marginal PDF of y. So I'll find the marginal PDF of x. So by definition, f of x equals, you integrate your joint with respect to y. So now I have to go think about integrating with respect to y. So I'm going to be looking at this particular x value, whatever that is. Imagine particular x value over here, for whatever x value, that's fixed x value, whatever that is. So I have to go integrate this over here, y value from this y value to that y value. So that's 1 for sure. The lower end, this is y equals x squared, so this is x squared. So whatever the x is, your y value is going from that squared to 1. So I'm getting my integration going from x squared 2, 1. The joint, which is 21 over 4 x squared times y, and I'm doing with respect to y. All right, so the rest is your work. So now that should be with respect to y. So I'm getting 21 over 4, so 21 over 8 x squared and y squared. So y value from x squared to 1. All right, so finally I'm getting 21 over 8 x squared, then 1 minus x to the 4th. So finally I'm getting this. According to this, my marginal PDF must be this, 21 over 8 x squared, 1 minus x to the 4th, for x value from where to where? I can see right there, -1 to +1. And 0 otherwise. Are we good so far? So it's all on you. So let's get the right expression. You can do the rest of it. So let's find the marginal PDF of y. So that's my f of y, and I'm integrating your joint with respect to x. All right, so imagine everything has to be in the support. Support is important to consider. So you have to go think about your support from, I think, the shape like this. So I'm trying to integrate your joint density with respect to x so that I'm going your x value from any x value for any given y, anyway, any given y, so y is right here. Any given y, you're integrating from this to this. So your x is, this is y equals x squared, so this must be negative square root of y. Oops. And this is positive square root of y. So now you're going into the lower bound to upper bound, and your joint 21 over 8 x is, where am I getting my mistakes? I have a joint. Joint is up there. 21 over 4 x squared y dx. So the rest is on you. You can do your work. So when you do the work, you will end up with 7 over 4, 7 over 2, 7 over 2, and y squared square root of y. So therefore, I have to write my marginal properly. So 7 over 2 y squared and square root of y for y values from 0 to 1 and 0 otherwise. All right, so that's your joint to marginal, both discrete and continuous case. I'm gone with this. So let's then moving on to the independent random variable. Let's get 352. independence one more time. We saw this long time ago. So let's get the definition. 3, 5, 2. So we're looking at this question as independent random variables. So we get independent random variables. What does that mean? All right, so two variables, x and y, are said to be independent if the probability that x is an element of a set A and y is an element of a set B equals the product. X is an element of A times y is an element of B. For every two set. A and B of any real numbers. So that's what it means by the definition. So every single set, the subset of real numbers, any part of the real number, your x is in that set, and at the same time y is in the set, I can do the product of individual probability. That's independence. So in a simple case, if you get a set A being from negative infinity to some number x, and your B can be from negative infinity to some number y, then when x and y are independent, the definition says the probability that x is an element of the set A and y is element of set B is the product of individual probabilities, which becomes probability that x is everything up to the number x less than or equals to x, and y is less than or equals to the number y. It's equal to x less than or equals to some number x, and y less than or equal to some number y. So that's what it means. So your left hand side is a joint PDF. So this is my definition, f of xy. This is the marginal and the marginal. So when x and y are independent, according to this is a joint CDF equal to, this is a marginal PDF, the CDF. So this is a product of the marginal CDFs. So that's what it means. I can separate them out. X alone and y alone. All right, so we will talk about this independence pretty often. So I want to go and write it simply. I don't want to write this independence all the time. So we often write this over here. Let's do this. Often it's written as your x variable is independent of your y variable. So that makes it a lot simpler to write. So that's what I'm going to be using. So that means x and y are independent. All right, so now that I have this, so that's exactly what I have in the theorem 354. It says your x variable and y variables are independent if and only if so I'm going to be writing it as IFF if and only if the future your joint fxy equals to the product of the marginal f of x times f of y. So I just did it anyway, so that's what summarizes for you. So that's one of the theorems, which is okay, but we have a lot better theorem, which is this theorem 3, 5, 5. So what it says, how do I identify something that is independent? So this is how. It says your x and y are independent if and only if they're independent, then your fxy, which is the joint PDF or PMF, let's just do PDF, it's common, equal to g of x times h of y for any non-negative function. G and H. So it says if x and y are independent, your joint PDF will become a product of g of x means function of x alone.
Ow.
And this function of y alone. So that's what the theorem is saying. It's very, very, very useful to identify if A and B are or x and y are independent. So if I know my joint PDF is a function of x alone and function of y alone, then I know they're independent. So that's how we're looking at it. All right, anyway, this is a general case of it. Now we can have the corollary, which is the specific case of it. So if I go 3 by 1, so if x and y are independent, a little more specific than this general f and g, f and h, if they're independent, if and only if your joint equals the product of the marginal for all these x and y. So that's another one that we're going to be using this. All right, let's go and so I'm going to be giving you kind of 3 examples to identify. So I'm going to be starting with my discrete case. So I would like to have a joint PMF of x and y. The question is, are x and y really independent? So let me show you the joint PMF. So I have x values and y values. So x over here and y in rows. X can be either 0 or 1. Y value can be 0 or 1. And the probability is 9 over 25 for 0, 0. And 0, 1 is 6 over 25. And 1, 0, which is 625 and 425. So this is my joint PMF. Are these x and y independent? Well, I have to check it. So I need to show for every single xy pair, fxy is equal to f of x times f of y for all xy pairs. So we have x 0, 1, y 0, 1. I have to get all pairs, so I have 4 different cases. So I have to think about all the possible cases of x and y 0, 0, 0, 1, 1, 0, and 1, 1. So what do I have to compare? I have to compare what is fxy, the joint, which is given 0, 0, 9, 25. 0, 1, which is 6 over 25, and I get them all. Oops. Then 1, 0, 6 over 25, and 1, 1, 4 over 25. So that's a joint that's given. What I have to check is f of x times f of y, the marginal. So let's get the marginal. We practiced a minute ago. So adding these two together, that should be your f is 15 over 25, which is 3/5. So this is my f of x of 0. And this, adding these two will get me 2/5. And this is my f of x of 1. So those are my marginals. And I can do the same for y values. So let's do the y values. Adding these two numbers together, that's 15 over 25, which is 3 over 5. So this is my f. Let's get some space. So this is my f of y of 0. And 2/5. Adding these two together, that's my f of y of 1. So I have a marginal. So I have to go get my f of 0, y of 0, so 0, 0, so 3/5 and 3/5. Are they equal? Yes, they're equal to each other. And I have to go check every single pair. So 0, 1, so 0, 1, x of 0, so 3/5. Y of 1, which is 2/5. So that's exactly the same. So are they equal? So we're checking this, every single one of them. Then the same way, so that should be 2/5 and 3/5. Are they equal? Yes, they're equal. And finally, we get 2/5 and 2/5. They're equal. So every single extra order pair, they're all equal to each other. The marginal, the product of marginal equals the joint. So therefore, I know the x and y's are independent. So that's how we check them. So let me just be clear. In your homework, the textbook example, 3, 5, 8, you can take a look at it. The question is, are x and y independent? And I don't want to go into the entire example, but you can read it on your own. Anyway, for this, your x values are either 0 or 1, and y values are 1, 2, 3, 4 in that example. So in order to show that x and y are independent, I have to go 2x values, 4 different y values. So 2 times 4 has to be many, many, many extra order pair to show that they're independent or not. But, well, if they're not independent, one of them may not be true. So one counter example is good enough. To show that x and y are not independent. That's easy to show. I just have to pick one that's not true, as it says. For example, in the book, f of 1, 1, which is 0.147 in the book. Then the marginal f of x of 1 and f of y of 1, it's 0.487 times 0.267. So they're not equal to each other. So that example is enough to show, therefore, X and Y are not independent. Not true. So that's easier. By showing that they're independent, you have to go through every single one of them. It's not that easy. It's a little tedious by doing it that way. Are we good so far? So this for discrete case. Now for continuous case is a little easier. So let's do this. So I want to go into the, let's do this way. So I want to go, let's do this same example. It's in the book, 3, 5, 11. So they're giving you the joint PDF of x and y as this. So f of xy equals to 2 times e to the power of negative x minus 2y for x 0 greater, y 0 greater, and 0 otherwise. Are x and y independent? All right, so I can go either way. Let's go two different ways, and one is easier than the other. So I can use the corollary over here. Well, if I know that they're independent, that this is true, or if that's true, then they're independent. So I can go figuring out the marginal times marginal. Is that equals to this? Then they're independent. So I can go through this. So this is the way. I can go another way. Let's get number one using the corollary. 3, 5, 1, showing that x and y are independent. You can only if the marginal equals, the joint is equal to the marginal, the product of the margin. Which, again, lots of details, but I'll just let you skip all the details. So I have to get my marginal f of x, which you will do, again, integration from 0 to infinity of this joint. Let me skip the whole work, but you will get something like this, e to the power of negative x. For x greater than 0, you can also get the marginal PDF for y, which is e to the power of negative 2y, I'm missing 2, for y being greater than 0. Show that your joint is the product of the two marginal. X and y are independent. So that's our way to go. However, we have a better way of doing this. So that's number 2, using the theorem. Which theorem? The theorem right here. This is the theorem says right here. 355. If your joint PDF over here is a product of any function of x alone, then x and y are independent. So in this case, using that theorem 355, can I write my joint PDF x times y, which is 2 times e to the power of negative x and e to the power of negative 2y. Can I write this as a function of x alone and function of y alone? And I can. According to this, I can call this is my function of x. And I can call this as my function of y alone. So in this case, if I can call x alone function 2 times this and y alone function then your joint is a product of those two, x alone and y alone. Therefore, your x and y's are independent. Got it. That's way simple. It doesn't require the margin PDF. I just have to get it and take a look at it. So this is very, very useful. So I'm going to be giving you 3 separate examples to use the theorem so that you can identify it on your own. So identify, so determine using the theorem if x and y's are independent given that you have a joint PDF. All right, here's my first one. The joint PDF is given as this. So fxy equals to some constant k, I don't have to know the k, but some number k, and times x squared times y to the 4th times e to the power of negative y times e to the power of negative x over 2. For x values greater than 0, y greater than 0, and 0 otherwise. So I'd like to know if x and y are independent. Well, I can see right away, so whatever the constant k is a constant. So whatever that makes it to be a joint PDF, doesn't matter what that is. So can I write this as a function of x alone and function of y alone? And it looks like I can do it. So I can see the part with x alone, so I can have my k somewhere, doesn't matter. So I can use these, x alone, and these for y alone. So I can call, well, why don't I go call g of x as the constant k, x squared, and e to the power of negative x over 2. And I can call hy, which is a y function alone, so y to the 4th, and e to the power of negative y. So I can write this joint PDF as a function of x alone and function of y alone. So therefore, then your joint is g of x, h of x. Done. Therefore, your x and y must be independent. So that's how you look at it. It's pretty clear when you look at them right away. So that's one. So let's moving on to B. Here's my joint. So fxy equals to 2/3 times x plus 2y for x 0 to 1 and y from 0 to 1 and 0 otherwise. So I'm trying to determine if x and y are independent, and I don't think I can write this as a product of x alone and y alone. So your joint, it cannot be written as a product of function of x and function of y. Not possible. I cannot separate them as a product of the x's with the y's. Therefore, your x and y are not independent. Cannot be independent. So it's pretty clear by looking at the whole joint density. Let me get the part C. So here's my f of xy, and it is 2 times e to the power of negative x and e to the power of negative y for 0, x is greater than 0, but less than or equals to y, and 0 otherwise. So I'm trying to determine if x and y are independent. Well, if I look at this whole density, the marginal PDF, it is some part of x alone and y alone. So it looks like, oh, isn't that the function of x alone and it's not the function of y alone. It looks like it, however, it's not exactly correct because but the support of x and y, they're not independent, they're related. Your x has to be smaller than or equals to y. So they're not independent. So that support suggests that your x and y's are not independent, so they're related. To be independent, you have to go get x and y both support totally separated, so one region is not depending on the other variable. Has to be totally separated. So that's how I know that they are independent or not independent. Very good. So let me then finish the last piece and I'll stop there and give you a break. So let's get the note. If x and y are independent, then some function of x and some function of y are also independent for any function. O, G, and H. So for example, if I know x and y are independent, for example, then x squared, which is function of x, and 2 times y, function of y, they're also independent. So that's what it means. All right, so this is about a good time to have a break. So any question you might have, stay behind and ask me a question. Otherwise, it's 7:27, so let's have about 8 minutes of break. So we continue at 7:35. 7:35?
Professor,
Yes.
can you go back to part A?
Which part? Part A? Here?
Yes.
Mm-hmm.
All right, thank you.
Mm-hmm.
Okay, you also go back down.
Down here? Let's start.
Yeah, all the way to the
Mhm.
bottom.
Mm-hmm.
Thank you.
Okay, it's a 7:35. So let's get to a new chapter. No section, sorry, new section. So we have finished the join distribution, joined PDF, PMF, the mass function, the density function, and the CDF. So we got all of those going back and forth. So now let's add 3.6, a conditional distribution. So you have to be very careful when you do the calculation of it. So let's remind you, what is this is about? It's a conditional probability. So let's recall when we have P, the probability that event A given event B. So I know that that's out of all B, so P of B in the denominator. Then the numerator is A and B happening together. A intersection B. So this is exactly what we're doing with the distribution. All right, let's get the distribution. Here we go. So for, in particular, let's get the discrete random variable case. So discrete random variables, x and y. So for example, I can think about this as a probability that your event A, which is x takes a number small x. So given this, so this is like event A. Given event B, so think of it as your y as a value number 1. So think of it as another event B, just like this. So that I know what it means by event A event here, and think of it as my B event, like this, A given B. So we are trying to get the probability of the denominator y equals to some number y, and the numerator must be the intersection of the two. So probability that x equals to small x and y equals to small y. So that you have this numerator, which is about x and y together jointly. So we write them down as the joint fxy, and your denominator, this is the y alone. So we call that the marginal, so f of y. So conditional, according to this, so this is a joint PMF over the marginal PMF. So that should be your conditional. So we are going to be using a notation. So that probability, we write this as, it's a function f, the probability that you get x given y. So f of x given y equals to, here we go, so this is my conditional PMF of x given y equals to the joint over the marginal PMF of, to be more exact, of y. Anyway, that's what this conditional distribution is about. So let's write the definition. So this is exactly what we did. So start with the definition of, let's say 361, it's discrete conditional distributions. All right, start from there. So I got my discrete case first of all. That's easier. So let's start with the definition of this. Definition 361 says So we have a joint PMF. So X and Y have a joint PMF. So that's f of x1. So we have f of x given y. Now you will notice later on which one is x, which one is y. So it's not as clear. So we tend to write your subscript x given y, so that when I see the numbers x and y, you will know exactly which one is which. So I'm going to be writing it as x given y. So that's what I'm going to be writing. Anyway, you'll know why. So that should be the marginal at the bottom and the joint on top over your given this, so given y, given, so that is your denominator, this marginal of what? F of what? Out of all the y's, I want x and y. So this is what it means. So of course, your denominator cannot be zero, so your marginal must be something positive. So this is how we define the conditional PMF. So this f of x given y, it is called the conditional PMF of x given y equals to some number. All right. So in a similar way, we can go f y given x. So we may write it as a subscript y given x. So in that order, so now it becomes the joint on top, and your denominator is out of all the x's. So that's marginal of x, f of x. And of course, the denominator cannot be zero, so something positive. So this is called the conditional PMF of y given x equals to some number x. So that's the definition. Anyway, I'd like to get you the notation in the book, the textbook. When you read a book, it's using, so in my case, we're using f of x given y. The book is using g of 1 and f of y given x. The book is using g2 of y given x. I don't enjoy that 1 and 2. I don't like this. I want to prefer it to be x given y or y given x. So I'm going to be using x given y and y given x. So anyway, what is this about? It's not that difficult if I go through the process of doing this. For example, if I have this conditional f of x given y, so x given, I want to pick a particular y value, given, let's say y value of 0. So that's my y value of 0. So that means your denominator is f of y of 0, which is a constant. It's a fixed number. It's a probability. In your numerator, your x can be any x, the joint x, the y has to be 0. So in the conditional, the 0, that's given 0. So that has to be fixed at 0, no matter what. So this is it. So in that sense, the denominator is, I want all these y value of 0. So what it means is I have to go get all these probabilities, add up together, x, y has to be 0 for all the x's to get the marginal, then the joint on top. So this is it. So this is your conditional. So the same way, let me just do it anyways. Let's get f of y given x and y given 0. What it means is your x is fixed at 0. So this is fixed 0. So this time this is your given. The x equals to 0. That's fixed. But y can be anything. So this means I'm getting my marginal fx of 0. It has to be a fixed. Then your x 0, y can be any number. So your denominator is a constant and this. So your denominator is, I want all these y values that add up together to get x0, but all different y values add up to get my marginal and the joint. And that's the idea of this conditional. Doing it is not as difficult as it looks like. So let me get the joint PMF case. Let's get joint PMF of x and y. So let me get you the table. So I have x values and y values. So your x's are either 0 or 1. Your y values are 0, 1, or 2. And let's give you the numbers. So I'm getting 10 over 50 for 0, 0, and 6 over 50 for 0, 1, and 4 over 50 for 0, 2. Then 15 over 50, then 10 over 50, and 5 over 50. All right, let's get this. So now this is my joint PMF. So start from A, what's conditional PMF? So let's find the conditional PMF of x given, let me fix y value at 0. So I want my PMF of x given y of 0. So let's get this. So what we need to do, we need to find f of x given y. So x can be what are the positive x values, but given y value must be 0. So the 0, that's fixed, it doesn't change, but your x's are either 0 or 1. So for x, 0 or 1. So that's what we're doing. So let me get this. So by definition, my conditional x given y, x given 0, your denominator must be the marginal fy of 0, and your numerator is f of x, comma, y has to be 0. Of this, let me get my denominator first, so I can get this right away. So f of y of 0, this is a marginal, so which means I want all these x values. X can be 0, x can be 1. So I want all the possible xy pair where x 0, but y has to be fixed at 0. So f of 0, 0, f of 1, 0, which, let me go back it up. It's a lot easier to consider this. So I have this x value of 0 and y value of 0. So this is it. So y has to be, this is what I want. I want the marginal of 0. So I want these two. together. Add up together. That's my f of y of 0. I want that. Let's add it all together. So that's what it means by adding those two numbers, which is 10 over 50 and 15 over 50. So that's 25 over 50, which is 1/2. So that's my denominator. So let's get this. I know what this is. So let me go get these individual values. So now I want f of x given y, x value of 0 given 0. I want this, and I want f of x given y, 1 given 0. What am I doing? Your x can be either 0 or 1. So I'm going to be changing this x value is either 0 or 1. So I have to get these individual values of it. So let's get it. So this one, I have the denominator already, which is 25 over 50. The sum of these two numbers in that column, I got this. The numerator, it's simply saying I want 0, comma 0. 0, comma 0 in that particular table, isn't that just this? 0, 0. So 10 over 50 out of the total column of this, well, that's basically it. So 10 over 50 out of 25 over 50. So it gets me 10 over 25, which is 2/5. Pretty much it. And I have the same thing, so let's get this, which means 25 over 50. The numerator, which is, but isn't that the other one also? The other one is this, right here. So this out of the total. So 15 over 50, let's get this. So this is about f of 1, 0. So 15 out of 50 over 25 out of 50, which is, again, 15 over 25, 3/5. So I get my entire conditional distribution. So what do? So I'm writing, therefore, my conditional distribution x given y value of 0 equals to, the probability is 2/5 for x value of 0, 3/5 for x value equals to 1. So we call this conditional PMF of x given y equals to 0. So remember, this is the distribution of x. So these numbers together, sum must be 1. It's a distribution. And these are the supports of that distribution. It's either 0 or 1. Are we okay so far? So technically, doing it, I can do it faster. Let's do it faster this time. So since I have it very similarly, I don't have an example. Let's get it similarly. It's very, very simple. So if I go f of x given 1, what does that mean? It means that, let me do it properly. I want x given y and x given 1. So I want to have my y values are fixed. So when y equals to 1, so I want to go back up to my entire table. Here we go. When the y value is fixed at 1, here's my y value of 1. I have a total probability of all of these all together. That's the marginal. And I want the joint. So 50 out of 50 over entire the total of these two. So I'm getting nothing more than sum of these two numbers together anyway. Let's write them out. This is going to be 16 over 50. So my conditional probability is nothing more than, again, 6 out of 50 over the marginal, which is 16 out of 50. So you get 6 over 16 for x value of 1. Then I can get the same thing for x value of 2, which is 10 over 16. I can reduce it, but let's leave it there. Are we good so far? So that's how we do. So what it means is, again, we are looking at out of the total these two, it's the total is marginal, that's what it is. Out of these, how much is that out of the total? That's a conditional. How much is this out of the total? That's a conditional. In the same way, I can do my conditional. The x, the y value of 2, out of these two, well, how much is that? That's a conditional thing. So check yourself, do it yourself. So I'm going to be writing them down just for you. If you have the x given y, x given y value of 2, you should be getting 4, 9 for x of 1 and 5, 9 when x equals to 2. So try to get it done yourself. And once you get it, it should be okay. But for now, it's a little confusing. But good so far. So now let's switch. So now I'm going to go back to the other way around. Let's find the conditional PMF of a y given x equals to 0. All right, so my conditional PMF of y says y given x. We want that. So y given x value of 0. So that means my denominator, it has to be the marginal x value of 0. Let's get all these together. Then the numerator, x is 0, y value can change. For what y values? Y value can be 0, 1, or 2. So that's what I see. So I'm looking at the conditional. Let's get the, first of all, f of x 0, which means in that distribution, now I'm going to be looking at this x value of 1. Let's clear that out. So that means my x has to be 1. It's fixed at 1. At 0, because it's 0. So it's fixed at 0. And the marginal must be some of these two numbers. So that's 10 plus 10, 20 over 50. That's a marginal. The conditional means this out of the total, and this out of the total, and this out of the total. So that's what it is. But anyway, first of all, let me get this f of x 0. The bottom one, if you do the math again, adding these two, that's f of x of 1. So let's get this. So what it means is I got add them up together. That should be, what was it? It was 20 over 50. So let me get you one. So for example, f of y given x, your y value, this is a distribution of y. So your y value can be 0, given 0. Your y value can be 1, given 0. And your y value can be 2, given 0. So your y value can change 0, 1, or 2. So that's my entire distribution. So therefore, out of 20 over 50, same thing, out of 20 over 50. So 20 over 50, the first one says a joint, 0, 0. So f of 0, 0, which is that f of 0, 0, 10 over 50. Then the next, we have second one here, which is 6 over 50. And the last one, which is 4 over 50. So I'm actually getting 10 over 20, 6 over 20, and 4 over 20. I can reduce it, but let's get it this as, let's make it to be the base 10, so 5 over 10, 3 over 10, and 2 over 10. So if I write it properly, my y given x, y given 0. So now this is a distribution of y. So I have to go get my probability for y value of 0 and for y value of 1 and y value of 2, which I have them all. 5, 10, 3, 10, and 2, 10. So a little trickier here and there by thinking about this, but as long as you get it cleared, then you should be able to process it. A little tricky again, but you should be getting this. So I wanted to check yourself when you have time. So you can also do f of y given x, and x being fixed at 1. So when you have time, check yourself. You should be getting 3 over 6, 2 over 6, and 1 over 6 for y of 1 and y2 and y value of 3. So that's conditional. Okay, then I think this is part B. I did part B, so let's get part C. Let's get the probability. Find the probability that your y value is less than or equals to 1 given x equals to 0. All right, let's get this. There are 2 different ways of getting this. For questions like this, number 1, I can do, well, let's use the conditional PMF. So this is about y given x. So I can make use of, well, let's use the PMF of y given x equals 0. So remember what this is f of y given x, and y can be any number, but x has to be 0. So I can make use of this, which is right here. So now I have this. Let me make use of that distribution, which I have it already. So I want to know y value less than or equals to 1. So what it means is, so that probability y is less than or equals to 1 given x equals to 0. So I can do the conditional probability y given x. Y can be 0, y can be 1. So I can do y can be 0 given x of 0, and also y can be 1 given 0. So I'm trying to see the y values of 0 or 1. So this is my 0, and that's y value of 1. Add it up together. Which I have them right here. So I have y value of 0, which is this, y value of 1, which is this. I want to add them up. So 5 over 3. Oh, 5 over 3, sorry about this. 3 over 5. 5 over 10. Sorry about this. 5 over 10 and 3 over 10. So 8 over 10. So that's how we do it. A little tricky. You have to be very careful when you do this. Well, this is one possibility. Number 2, you can use this regular probability for discrete case. So for example, the probability that y is less than or equals to 1 given x equals to 0. So think of it as a conditional probability. The denominator is probability that x equals to 0. The numerator, x is 0, but your y is less than or equals to 1. I can do it. So in this case, your x0, y can be 1 or 0, so it has to be 0 or 1. So I have to add all the joint probabilities. Denominator, x has to be 0, but your y has to be, can be anything from 0, 1, or 2. So let's add them up together. So that's what it is. So when you do this, I'll let you do the math. So 20 over 50, which is a marginal anyway. And your numerator, I can use the joint 10 over 50 and 6 over 50, which is 16 over 20, so 40. Can be done. There are lots of thinking that involved. You have to be a little careful. So let's write a note. The conditional PMF is a proper PMF. So that when I get my f of x given y is a distribution of x for any given or fixed y value. So y is fixed, that's fixed. Your x can be whatever x positive x value is. Therefore, if you add your x given y, for all these x values must be 1. In the same way, you get this f of y given x. So that's fixed x value, it doesn't change. But your y can change, so this is a distribution of y. So if I'm adding all these y given x, all these y values must be 1. What does that mean? It means something that we already did it. What does that mean? Well, this is what it means. Here's my conditional. So for fixed x value of 0, you're adding all these y values of 0, 1, and 2. So sum of all these numbers must be 1 because it's a proper PMF. That's what it means. Nothing else. So every single conditional PMF, the sum must be 1, every single one of them. If you don't get it, something is not right. So that's simply what it says. Nothing more than that. How are we doing? Again, you have to be thinking pretty carefully and clearly. Let me get you a few more example of continuous case and I'll stop there. So you have to really, really practice and study a lot of this to be clear. Not difficult, but it's confusing. Let's get the continuous case. 362. Continuous conditional distribution. All right, let's get a continuous case. So let me get with the definition. So your definition 362. 2. So now we have a joint PDF. So x and y have a joint probability density function. So it's continuous case. The conditional PDF of x given y equals to y is defined as below. It's exactly the same as before. It is defined as, here we go, x given y is, again, I'm going to be writing x given y. The marginal f of y in the denominator and the joint. And the same way, the conditional PDF of y given x is the following. So y given x. So we write it as y given x. The marginal of x, the denominator and the joint on top. So it's a definition. So let me get one example, then I'll be done for today. So let's get the case. So I have a joint PDF of x and y.
Sorry, can you scroll up a little bit?
There.
Okay, I'm good.
Mm-hmm. So definition itself, it's exactly the same as this case over the discrete case. It's the same thing, but what we have to do is a little different because we don't add anymore. Let's get them all. So let me get you the joint PDF. Here's my fxy, which equals to 1 over y and e to the power of negative x over y times x over y times e to the power of negative y for x greater than 0 and y greater than 0 and 0 elsewhere. All right, let's do some work here. So let's find the conditional PDF of x given y equals to the number y. All right, so let's get the definition. It says f of x given y, so x given y must be equal to the marginal of the joint on top and the marginal of y in the denominator. So first step is I have to go get this. I need to go get the marginal. So let's get the marginal. So I'm going to be getting f of y, which is, by definition, you integrate your joint with respect to x. Then I have to think about the support. Do I have to worry about this region? Is it rectangular shape or not? So I have to go think about the support, which is, well, in this case, it's not very complicated. It's about x and y are both 0 to infinity. So your support is nicely formed. So that's my support. So integration is pretty simple in this case. So now I have to go, well, this is negative infinity to positive infinity by definition. So now I have to go get my dx. So x is going from 0 to infinity. So now I have to go get this. from 0 to infinity of the joint, which is 1 over y, and e to the power of negative x over y, and times e to the power of negative y dx. You been me so far? So that's it. So the rest, well, you have to do it on your own, but I can take that one part out. So that has nothing to do with x anyway, so I can take it out. I can even take out this 1 over y, but let's leave it there. Anyway, I'm going to be doing e to the power of negative y, and the rest, 0 to infinity, 1 over y, and e to the power of negative x over y dx. If you do some work on your own, this whole thing integration, that will be 1. So I'll let you do that. So if you do that, that's going to be 1, which means your marginal PDF of y equals to e to the power of negative y. So now I'm ready. Let's go back to my definition. The definition says f of x given y, x given y, I need the marginal, which is e to the power of negative y, and the top, I need a joint. So let me copy the entire joint, which is 1 over y. And we have e negative x over y times e to the power of negative y. So that's gone. So I'm getting 1 over y e to the power of negative x over y. So I have to write it properly according to this. Therefore, your conditional PDF of y given x, or x given y, equals to 1 over y e to the power of negative x over y. So this is your x value greater than 0, and 0 other y's. So remember, it's conditional, so that's fixed, the fixed number. So this must be the distribution of x. So y is a fixed number, it's a constant. X is a variable, the random variable. That's what I have to think about. So this is it. So I'm looking at this conditional PDF, and let me give you an example. What does that mean? If I pick one particular x value, for example, let's get x given y, and I'm going to be picking y value of 2. For example, if y happens to be 2, then in that conditional PDF, the y value, that's going to be 2, and that's going to be 2. So I'm getting 1/2 e to the power of negative x over 2 for x value greater than 0 and 0 otherwise. So this, again, for a given x value, you might notice again the distribution of x. It's a PDF. So this is going to be the graph of this, such that that entire area under that conditional PDF always 1. So this is it. All right. So far, so you have to be a little careful. What is y? What is it? What's fixed? What's not fixed? So this is an exponential distribution. We see this pretty often. Anyway, I got this. So let me get a probability and then I'll be stopping there. Let's get the question. This was A. Let's get my B. So I want to find the probability that x is greater than 3 given y equals 2. So for this, I have to use a conditional PDF. So we need to use the conditional PDF of, according to this, x given y equals 2. So we have to do that. So here goes x given y of this. The conditional PDF of x given y equals 2, which means we need to use f of x given y has to be 2. So we need that. Which I just did it right here. So that's what it is. So let's get the probability of x greater than 3 given y equals to 2. So that conditional PDF, I saw the density function already. It looks like this. This is my x. So this is f of x given y value is fixed at 2. So I want the probability that your x greater than 3. So your x, 3 somewhere, I need to go get this probability, which is the area I've integrated. So that means, well, here we go. I have to go integrate my conditional PDF from 3 to infinity of that function, which is 1/2 e to the power of negative x over 2 dx. Which, I'll let you do it. So this is going to be e to the power of negative 3 over 2. So let me stop here. I think I've done enough. So it's a little trickier than before, so you might want to go and do a lot of practices and see where you're getting it, or you're confused or not confused. So, right? So let me stop. Any question you have, you stay behind. Otherwise, I'll see you tomorrow.
Professor, could you scroll back up, please?
Up here? Or the up more?
Yeah, a little more.
A little more? Mm-hmm.
A little